Okay, so this is the second part of our lecture on continuous probability distributions. We took the second example, and this is a third example. The marks of 500 candidates in an examination are normally distributed with mean of 45 marks and a standard deviation of 20 marks. So if 20% of the candidates obtain a distinction by scoring X marks or more, estimate the value of X. So this is a little bit different from what we worked in the last video. So let's get our parameters. Our mean is 45. Our sample size is 500, and then the sigma value, that's the standard deviation, is equal to 20. So we are interested in the probability of X greater than small x, and that probability is 20%. 20% is the same as 0.2 if you divide 20 by 100. So we get probability of X less or equals to X should be equals to 1 minus 0.2, which is equals to 0.8. So all we want to do now is to read a value, that is the Z value in the normal distribution table, that will give us a probability of 0.8. So formally we have Z greater than X minus 45 over 20 is equals to 0.8. So we want to read the probability value, p value of 0.8 from the normal distribution table. Okay, this is the normal distribution table. So we have the Z values, some here, that is here. So those on the vertical axis, that is the first digit and the first decimal point, and then this group, that is the second decimal group. So how do we get 0.8 from the table? We have to look around everywhere. So we can see here we have 0.9, 0.79955, 0.8023. So we cannot get exactly 0.8 from here. So what we're going to do is to read a value, get a value that is much closer to 0.8 than any of the numbers. So if you take 0.799, you realize that the difference is lower than if you take 0.80234. So 0.799, this one here, is much bigger, sorry, is much lesser than if we decide to use the 0.8. So we are going to go with this one here. Okay, so if that is done, then we can now circle this and then trace it upwards, trace it to the left, and then read those two values, add them together. So we have Z is equals to 0.8 plus 0.04, and that will give us 0.84. So from the normal distribution table, reading 0.8 from the table, we get a Z value to be equals to 0.84. So our probability of Z greater than 0.84 is equals to 0.8. But then x minus 45 over 20 is what is equivalent to the 0.84. So we want to make x the subject from here. Alright, so we have x minus 45 equals to 0.84. Multiply this by 20. So our x, make x the subject, is equals to 45 plus the product 0.84 multiplied by 20. So if using your calculator, this should give us approximately 61.8. So this is the value of x. The weight in grams of the beans in a thing is normally distributed with mean mu and standard deviation 7.8. Given that 10% of the tins contain less than 200, find the mean weight of beans in the tin. So with this, it's similar to the third example that we just worked, except that this time we are not looking for x, we are looking for the mean, but we go through the same procedure. So we're going to say z is equals to 200 minus mu, which is not known, all over 7.8, our standard deviation. So we want to find the probability that x is less than 200. That will be 0.1, 10%, remember that. So if our z less than the one we are going to calculate, if that is equals to this, then we can find this again in the negative table, which we don't have. So we're going to use 1 minus what we're going to read on the positive table. So that is equivalent to say 0.1, which is equals to 0.9. So as we read in the first case, we are looking for 0.9. Then if I start from here, there's 0.90147, and this one here, I think I would consider these two and then try to find the difference, and you would realize that 0.89973 is much closer to 0.9 than 0.9017. So we would read this and then go up, come to the left, and pick what we have at the very top. So our z value is equals to 1.2 plus 0.08, and that will give us 1.28. So our z value is 1.28. Let's come back here. So we have z from the table is equals to 1.28, but then that would be the negative counterpart. So we are going to use the negative instead of the positive. So probability of z less than negative 1.28, it's what gave us the 0.1. So again, 200 minus mu all over 7.8 is the z value that we have just read in the table, and that is equivalent to negative 1.28. Let's do the mathematics. Multiply here 7.8, do the same thing to the right side, 7.8, and then you make mu the subject. So mu is equals to 200 plus 1.28 multiplied by 7.8. So together we have 209.9, so approximately 210 grams. So this is how we solve this question. The second part of the question says, given that 10% of things contain less than 200, find the percentage of things that contain more than 225 grams of beans. So here again, we're not interested in the mean, we're not interested in the x, we're interested in the percentage. So let's see. So the percentage of beans greater than 225 grams, we say z, let's call it calculated, is equals to 225 minus what we have gotten, the mean that we got, all over 7.8 as a standard deviation. So this should give us 1.92. Can be wrong, so point your calculators and be sure that is the right thing. So P of x greater than 225 is equals to z less than the z that we have just calculated. What would be that probability? So we say this is equals to 1 minus the probability of z less than z calculated. Remember, the question is x greater than. So this, we read this from the table, the 1.92 that we got. Now at this time, it is not going to be, we are not going to look for 1.92 inside the plenty values and trace them upwards, outwards. We are now going to look for two things. One, the first digit and the first decimal, that is 1.9, and then second, the second decimal, that is 0.02. If you add this plus 0.02 is what we have inside the bracket 1.92. So let's head on to the table and get this value, probability value. Okay, we are here. So we are looking for z equals to 1.92. So the first two is 1.9, and then 1.9 is below. So let's go down. Okay, so 1.9 is here. Then the next one is to look for 0.02, and 0.02 is the third column after the z. So let's go back there and here. That is our probability value. Let's go back and then put this back in. So reading this is equals to 0.97257. So 1 minus 0.97257 will give us approximately 0.0274, and in terms of percentage we just multiply that by 100, and that will be 2.74. Now let's talk about normal approximations to the binomial distribution. If you have a binomial question and then your n is large, your x is large, it becomes difficult to go through all of these. Why? Because the binomial is looking at number of x's in n trials. So n choose x, p to the power x, 1 minus p to the power n minus x. So you can imagine having n to be 200, and you are looking at x is equals to, let's say, Okay, let's just say x greater than 100. So from 100 to 200. So you are going to be having probability of x equals to 100 plus 101 plus all the way up to 200. I don't know how long or how patient you can be to get this done. Fortunately, there is a way out, and that way out is to approximate the answer using the normal distribution function. And what are the circumstances? One, when we have the sample size multiplied by the probability of a success, and that is equals to 5 or greater than 5, then using the normal approximation we should get approximately the same value as using the binomial. And the second condition is if we multiply the same n value by the probability of a failure and get more than 5 or equals to 5, then we can again use the normal approximation. Now with the normal approximation, the normal distribution, we need the mean and we need the standard deviation. If the question is given in a binomial form, how do we get the mean and how do we get the standard deviation? This is how we get the mean. The sample size multiplied by the probability of success is equals to the mean. Then the square root of the sample size multiplied by probability of a success and multiplying that by the probability of a failure. If you take the square root of that, that is equivalent to the standard deviation in the normal distribution function. So we use these approximations to get the answer for the probability value. For example, texting while driving can be dangerous, but young people want to remain connected. Suppose that 26% of teen drivers text while driving. If we take a sample of 500 teen drivers, what is the probability that the survey results differ from the truth about the population by not more than 3% of points? So this is clearly a binomial case where our P, probability of a success, is equals to 0.26. Our sample size is equals to 500. And then our standard deviation, we can get that unless we derive it from the P and the N. So if you look at the sample size 500, if you multiply that by 0.26, we are obviously going to get more than 5. That is the condition to use the binomial approximation, the normal approximation to the binomial distribution. So let's find the proportion. The last part of the question is talking about not more than 3% of points. Right, so if that is the case and the probability of a success is 0.26, then we should be looking at the following proportions. The lower proportion is going to be 0.26 minus 0.03, and the upper is going to be 0.26 plus 0.03. So that will be 0.23 and then 0.29. So this will define the limits or the boundaries for us to use in the normal case. Let's find the standard deviation, which is equals to 0.26 multiplied by 1 minus 0.26 all over 500, and we take the square root of that. So this is equals to 0.00385, and if we take the square root of this, we should get approximately 0.003 0.0196. So we calculate P between 0.23 less or equals to the estimated value of P less or equals to 0.29, and this we put in the normal the Z's formula as 0.23 minus 0.26 all over 0.0196 less or equals to Z less or equals to 0.29 minus 0.26 all over 0.0196. We estimate the 0.23 minus 0.26 over 0.0196 to be negative value 1.53 less or equals to Z less or equals to 1.53, and that is equals to the probability of Z less than or equals to 1.53 minus the probability of Z less or equals to negative 1.53. If you remember, we said the integral over the range a and b is the area between a and b. So this is cumulative. So to get that of b less or equals to b, a would have included. So let's say if we are starting from 0 and we want b, we go all the way from here to b to get the probability of z less or equals to b. If we want a, then we go all the way from here up to a. So to get in between a and b, we simply have to subtract this from that we obtain from b, and that will be equivalent to the area that is between a and b. So that is exactly what we have just done here. So if we refer back to the table, the normal distribution table, 1.53 will give us a probability value of 0.93701 minus probability of a negative 1.53. So again, if you don't have the negative part of the normal distribution table, you can read it as a positive and subtract it from 1. So this is equivalent to saying we are reading a negative 1.53. So that will give us 0.0630. So do the subtraction and we will get 0.874. So this approximately it's 87.4%. Example number 6. In a large-scale survey concerning the use of female contraceptives, about 40% of female students were reported to have used contraceptives regularly. In a future sample random of 150 female students, let X be the number of female students who used contraceptives. Approximate the probability that X is between 52 and 71 inclusive. So this is another case of the normal approximation. So first we are to estimate. This is a binomial case. So we have X is binomial with 150 trials and the probability of success equals to 4. So we simply want to convert this, use the normal distribution to approximate this answer. So we have probability of X being between 52 and 71. So if we were to use the binomial case, we will have to do probability of X equals to 52 plus 53, 54 up to 71, and that is going to be a very long way. So thank God to the approximation method. So we simply have to estimate our mean, which is equals to NP, and N is 150, P is 0.4, and this will give us 60. Then again, we estimate our standard deviation, which is equals to square root of 150, our sample size, 0.4, the probability of a success, and then 1 minus 0.4, the probability of a failure, and this should give us 6. Now, because of the approximate continuity, we will have to subtract half from the lower and add half to the upper end, and that will give us probability of 51.5 less or equals to x less or equals to 71.5. So this will be equals to probability of 51.5 minus 60 divided by 6 less or equals to x minus 60 all over 6, and this is our z value, our z calculated value. So less or equals to 71.5 minus 60 all over 6. With the help of our calculators, we get the left side to be negative 1.42 less or equals to our z value less or equals to the right side will be 1.92. So again, we are going to use the upper limit minus probability of the upper limit minus probability of the lower limit. So we have P of 1 point, Z less or equals 1.92 minus P of Z less or equals to negative 1.42. So the probability value for the Z less or equals to 1.42 is equals to 0.9726, and the negative 1.42 is 0.0778. Do the subtraction, we are left with 0.8994. So this is the probability that x is between 52 and 51 inclusive. The last but not the least is to approximate the probability that x is greater than 67. So this, we have x greater than 67. Now let's note that here 67 is not included in the range. So by the approximate continuity, we simply have to add 0.5 to this, so that we get probability of x greater than 67.5. This is what we need to do. So this is equals to P as a probability, x less than 6, x minus 60 all over 6, our standard deviation, greater or equals to 67.5 minus 60 all over 6, and this, we are going to read this from the table, and the table is cumulative, so that means it's going to be less or equals to but not greater than. So if we write this as z, find this value, and we get 1.25 greater or equals to 1.25, this should be equals to 1 minus the left side of it, so x less than 1.25. So this is what we are going to read from the table and subtract it from 1 to get this. So from the normal distribution table, this value here, it's equals to 0.8944. So let's put that back. So we have z greater or equals to 1.25 is equals to 1 minus 0.8944, and that will be 0.1056